Dengan PLN Mobile, semua makin mudah. Download aplikasinya sekarang juga. PLN, Power Beyond Generations.
Corporations can use two approaches to increase value: maximizing revenue and reducing cost. PLN is also expected to reduce cost and increase operational efficiency. Enterprise Asset Management, or EAM, is an important instrument to improve efficiency, especially during transmission and distribution. There is an abundance of data and information that must be integrated to make real-time decisions accurately. With EAM, PLN can aim to reduce operational and maintenance costs by up to 1.3 trillion IDR for distribution and 419 billion IDR during transmission activities by 2024. EAM is achieved through integrated maintenance from planning, execution to budget utilization, with the target of reducing the duration of blackouts within 1 year. This method can reduce unplanned outages, which inevitably lead to increased cost and decreased customer trust. To accelerate accurate decision-making, data and operational and maintenance activities are converted into digital form with easy-to-understand visualizations. This allows PLN to provide reliable and high-quality electricity. In addition, PLN is developing a real-time loss monitoring initiative, aiming to reduce potential energy loss that can save up to 562 billion IDR by 2024. Real-time loss monitoring is PLN's effort to reduce potential loss of electrical energy from upstream to downstream due to leakage. Mitigating energy leak will improve the quality of analysis and accuracy of each energy transaction. This gives PLN the potential to earn an additional revenue of 37 billion IDR per year by 2024 at a B2B rate. By providing services without power outages and no flicker.
Transformasi PLN, Power Beyond Generations.
Universitas Gadjah Mada, or UGM, is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, we learn by continuously exploring sciences, learning from history, observing the present, and researching for the future. We always work hard and never give up. The learning and research processes at UGM continue to run together and explore state-of-the-art innovations. To create a convenient, environmentally friendly, and pollution-free green campus, UGM has built a wisdom park that substantiates the teaching and learning process. The park per se is open to the public. UGM has also developed drinking water facilities throughout the campus, provided by Drinking Water Supporting Unit. This system is harnessed by the entire academic community of UGM. As the manifestation of its teaching endeavor, UGM operates various field laboratories for educational and research purposes. Furthermore, UGM has established and run a science technopark as an embodiment of its capability of inventing and commercializing a myriad of innovative health products, ranging from medical devices, herbal medicines, and healthy food.
There are now more than 118,000 cases in 114 countries, and 4,291 people have lost their lives.
2020 has been a tough year for anyone, and it is no exception for UGM. Campus activities are abruptly halted, student activities on campus are annulled, and everyone is forced to work, worship, and study from home. Lecturers have no choice but to learn how to teach effectively using the information and communication technology or ICT. Learning and research on technology are strongly supported at UGM, and in fact, we have conducted various cutting-edge technological research. Community Service or KKN is one of the most important courses to complete the study program, which will be undergone by University of Gadjah Mada or UGM in 2020 while adopting online courses system. Supported by the Ministry of Education, UGM will continue its service within the society across Indonesia during the pandemic issue. Lecturers and researchers at UGM continue carrying out basic and applied research in many realms. For instance, studies in the health sector to cope with COVID-19 are being encouraged and accelerated as a form of UGM's commitment to mitigating disaster using scientific methods. One of the most innovative inventions regarding to mitigating the COVID-19 is Genos, a screening tool or early detector of patients exposed to COVID-19, which is able to identify the symptom through exhale within 80 seconds. Genos is highly reliable. It has a number of advantages as a COVID-19 fast detection tool. Its sensor is able to detect more than thousands of patients in the long term, while providing relatively fast results, non-invasive and affordable. In addition, its usage also applies non-rebreathing mask and disposable HEPA filter. Those challenges somehow direct or even force us to innovate and modify approaches. Success is a journey which necessitates smart work through learning, studying, and sacrificing. Despite all that, most of all, We love what we do.
Government has embarked on the path to an electric vehicle ecosystem by launching the Battery Electric Vehicle Program, or KBLBV. To accelerate the program, the State Electric Company, PLN, has developed an application called Chargin, the first app to support the electric vehicle ecosystem in Indonesia. Chargin controls and monitors electric car or motorbike battery charging at public electric vehicle charging stations, or SPKLU. Chargin is easy to use. Users can directly download the app onto their smartphones and manage their balance via the Link Aja payment platform. Chargin will guide the user to the nearest SPKLU location. At SPKLU, connect the charger to the vehicle's electrical charging inlet. Open the Chargin application and select the charging menu. Then, scan the barcode that is located at the top of the charger connector. Enter the amount of kilowatt hours to purchase. Click reservation, then confirm the charging. The light indicator on the charging connector will turn on and then turn off once the charging process is complete. Chargin makes charging electric vehicles easier and more practical, convenient, and efficient.
Kalau Anda ingin memanfaatkan SPKLU atau stasiun pengisian kendaraan listrik umum milik PLN, itu bisa dengan aplikasi Charge-in yang bisa di-download di Google Play Store. Di situ ada lokasinya SPKLU PLN itu di mana aja dan mesin yang masih ready di mana. Dan kalau Anda register, nanti Anda bisa dapat barcode dan tinggal scan-kan barcode tersebut ke SPKLU dan Anda bisa menge-charge mobil listrik Anda.
Transformasi PLN, Power Beyond Generations.
Mobile, semua makin mudah. Download aplikasinya sekarang juga. PLN, Power Beyond Generations.
Corporations can use two approaches to increase value: maximizing revenue and reducing cost. PLN is also expected to reduce cost and increase operational efficiency. Enterprise Asset Management, or EAM, is an important instrument to improve efficiency, especially during transmission and distribution. There is an abundance of data and information that must be integrated to make real-time decisions accurately. With EAM, PLN can aim to reduce operational and maintenance costs by up to 1.3 trillion IDR for distribution and 419 billion IDR during transmission activities by 2024. EAM is achieved through integrated maintenance from planning, execution to budget utilization, with the target of reducing the duration of blackouts within 1 year. This method can reduce unplanned outages, which inevitably lead to increased cost and decreased customer trust. To accelerate accurate decision-making, data and operational and maintenance activities are converted into digital form with easy-to-understand visualizations. This allows PLN to provide reliable and high-quality electricity. In addition, PLN is developing a real-time loss monitoring initiative, aiming to reduce potential energy loss that can save up to 562 billion IDR by 2024. Real-time loss monitoring is PLN's effort to reduce potential loss of electrical energy from upstream to downstream due to leakage. Mitigating energy leak will improve the quality of analysis and accuracy of each energy transaction. This gives PLN the potential to earn an additional revenue of 37 billion IDR per year by 2024 at a B2B rate. By providing services without power outages and no flicker. Transformasi PLN. Power beyond generations.
Universitas Gadjah Mada or UGM is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, we learn by continuously exploring sciences, learning from history, observing the present, and researching for the future. We always work hard and never give up. The learning and research processes at UGM continue to run together and explore state-of-the-art innovations. To create a convenient, environmentally friendly, and pollution-free green campus, UGM has built a wisdom park that substantiates the teaching and learning process. The park per se is open to the public. UGM has also developed drinking water facilities throughout the campus, provided by Drinking Water Supporting Unit. This system is harnessed by the entire academic community of UGM. As the manifestation of its teaching endeavor, UGM operates various field laboratories for educational and research purposes. Furthermore, UGM has established and run a science technopark as an embodiment of its capability of inventing and commercializing a myriad of innovative health products, ranging from medical devices, herbal medicines, and healthy food.
There are now more than 118,000 cases in 114 countries, and 4,291 people have lost their lives.
2020 has been a tough year for anyone, and it is no exception for UGM. Campus activities are abruptly halted, student activities on campus are annulled, and everyone is forced to work, worship, and study from home. Lecturers have no choice but to learn how to teach effectively using the information and communication technology, or ICT. Learning and research on technology are strongly supported at UGM, and in fact, we have conducted various cutting-edge technological research. Community Service, or KKN, is one of the most important courses to complete the study program, which will be undergone by University of Gadjah Mada, or UGM, in 2020 while adapting online courses system. Supported by the Ministry of Education, UGM will continue its service within the society across Indonesia during the pandemic issue. Lecturers and researchers at UGM continue carrying out basic and applied research in many realms. For instance, studies in the health sector to cope with COVID-19 are being encouraged and accelerated as a form of UGM's commitment to mitigating disaster using scientific methods. One of the most innovative inventions regarding to mitigating the COVID-19 is GENOS, a screening tool or early detector of patients exposed to COVID-19, which is able to identify the symptom through exhale within 80 seconds. GENOS is highly reliable. It has a number of advantages as a COVID-19 fast detection tool. Its sensor is able to detect more than thousands of patients in the long term, while providing relatively fast results, non-invasive and affordable. In addition, its usage also applies non-rebreathing mask and disposable HEPA filter. Those challenges somehow direct or even force us to innovate and modify approaches. Success is a journey which necessitates smart work through learning, studying, and sacrificing. Despite all that, most of all, we love what we do.
Government has embarked on the path to an electric vehicle ecosystem by launching the Battery Electric Vehicle Program, or KBLBV. To accelerate the program, the the State Electric Company, PLN, has developed an application called Chargin, the first app to support the electric vehicle ecosystem in Indonesia. Chargin controls and monitors electric car or motorbike battery charging at public electric vehicle charging stations, or SPKLU. Chargin is easy to use. Users can directly download the app onto their smartphones and manage their balance via the Link Aja payment platform. Chargin will guide the user to the nearest SPKLU location. At SPKLU, connect the charger to the vehicle's electrical charging inlet. Open the Chargin application and select the charging menu. Then, scan the barcode that is located at the top of the charger connector. Enter the amount of kilowatt hours to purchase. Click reservation, then confirm the charging. The light indicator on the charging connector will turn on and then turn off once the charging process is complete. Chargin makes charging electric vehicles easier and more practical, convenient, and efficient.
Kalau Anda ingin memanfaatkan SPKLU atau stasiun pengisian kendaraan listrik umum milik PLN, itu bisa dengan aplikasi Charge-in yang bisa di-download di Google Play Store. Di situ ada lokasinya SPKLU PLN itu di mana aja dan mesin yang masih ready di mana. Dan kalau Anda register, nanti Anda bisa dapat barcode dan tinggal scan-kan barcode tersebut ke SPKLU dan Anda bisa menge-charge mobil listrik Anda.
Transformasi PLN, Power Beyond Generations.
Mobile, semua makin mudah. Download aplikasinya sekarang juga. PLN, Power Beyond Generations.
Corporations can use two approaches to increase value: maximizing revenue and reducing cost. PLN is also expected to reduce cost and increase operational efficiency. Enterprise Asset Management, or EAM, is an important instrument to improve efficiency, especially during transmission and distribution. There is an abundance of data and information that must be integrated to make real-time decisions accurately. With EAM, PLN can aim to reduce operational and maintenance costs by up to 1.3 trillion IDR for distribution and 419 billion IDR during transmission activities by 2024. EAM is achieved through integrated maintenance from planning, execution to budget utilization, with a target of reducing the duration of blackouts within 1 year. This method can reduce unplanned outages, which inevitably lead to increased cost and decreased customer trust. To accelerate accurate decision-making, data and operational maintenance activities are converted into digital form with easy-to-understand visualizations. This allows PLN to provide reliable and high-quality electricity. In addition, PLN is developing a real-time loss monitoring initiative, aiming to reduce potential energy loss that can save up to 562 billion IDR by 2024. Real-time loss monitoring is PLN's effort to reduce potential loss of electrical energy from upstream to downstream due to leakage. Mitigating energy leak will improve the quality of analysis and accuracy of each energy transaction. This gives PLN the potential to earn an additional revenue of 37 billion IDR per year by 2024 at a B2B rate. By providing services without power outages and no flicker.
Transformasi PLN, power beyond generations.
Hi, good morning. Can you hear me?
Good morning. Okay. Hello. Good morning.
Hello,
Yeah.
am I audible?
Yes.
Yes. I can hear you.
Okay, good. Thank you.
Yes.
So, how much time we have? Another 5 minutes?
Okay. Let me contact our moderator. Anyone can help us here, the moderator or the committee, to mention how many minutes the speaker can speak?
No. What time we start? Is it at 10:10?
Yes, at 10. It's about 5 minutes to go.
Okay, fine. Thank you.
Thank you.
Kita play mantap itu Pak. Oh iya, aku play ini video.
Universitas Gadjah Mada or UGM is a public university renowned as the People's University, which strives for and puts forward the interests of the citizens and nation of Indonesia. As a higher education institution that has long been recognized by the society, we are proud of our timeless and tireless dedication to the nation. By cultivating, implementing, and leveraging education, research, and community services, which constitute the salient objectives of Indonesian higher education, or Tridharma, we remain committed to incessantly promoting the values of Pancasila. We exert the utmost effort to protect Indonesia's sovereignty in accordance with Pancasila ideology and the 1945 Constitution. As a world-class university, UGM is devoted to the interests of the nation and humanity. We conduct research, provide education, and deliver community services by enhancing knowledge that benefits the community, the nation, and the world. We have been learning from one another and get stronger together since we believe that knowledge is not useful unless it is shared with others. The learning process will never cease developing. At UGM, we learn by continuously exploring sciences, learning from history, observing the present, and researching for the future.
Distinguished speakers, moderators, and all participants, welcome to the third International Conference on Technology and Policy in Electric Power and Energy. Good morning, ladies and gentlemen from all around the world. This is the second day of this conference, and yesterday we have had our keynote speakers from Ministry of Education, Culture, Research and Technology, Professor Edward from Auburn University, US, Professor Joseph M. Guerrero from Albert University, Denmark, and Professor Andrew Blackers from Australian National University. Ladies and gentlemen, I am Santi Zaidan. It's been a very great honor for me to be able to say hi and greet everyone as the master of ceremony this morning. We are now live from Universitas Gadjah Mada, Yogyakarta, Indonesia. Right now it's 10 a.m. Indonesia time, GMT +7. I also would like to say good afternoon or good evening for ladies and gentlemen or participants who live in other countries. Thank you very much for your support and participation. Distinguished guests, ladies and gentlemen, this conference is a platform for policymakers from government, researchers from national and international energy research institutes, academicians from universities, as well as managers and engineers from the industry to share ideas and research results that are related to these issues. And to begin this conference, ladies and gentlemen, today we are going to have our speakers from National University Singapore and Nusya University India to join us right now. For those speakers, we will have our moderator to lead the session. Inviting our moderator, Mr. Husni Rois Ali, to lead the session. But before I invite our moderator, let me introduce our moderator, Mr. Husni Rois Ali, finished her doctoral degree in Department of Electrical and Electronic Engineering, Imperial College London, and then he also got his Master Engineering, Department of Electrical Engineering, Chulalongkorn University, Bangkok, and also he finished his Electrical Engineering in Gadjah Mada University, Indonesia. So once again, ladies and gentlemen, inviting our moderator, Mr. Husni Rois Ali, to join us on the screen.
Okay, thank you very much, MC. Can anybody hear my voice clearly?
Of course, yes.
Okay,
we can hear you clearly.
Okay, I think we should start now. Very good morning, ladies and gentlemen. First of all, I would like to welcome you in the second day of the conference, International Conference on Technology and Policy in Energy and Electric Power, ICT-PEP 2021. My name is Ali from Universitas Gadjah Mada, and I will be the chair of this section. In this section, we're going to have two presenters. The first one is Professor Sanjeev Kumar Panda from the National University of Singapore and US, and the second one is Professor Ankush Ghosh from Newtia University, India. Before we start, I would like to mention a couple of housekeeping notes. First of all, for each presenter, there will be around in total 30 minutes for his presentation, and after that there will be around 10 minutes question and answer session after each speaker concludes his presentation. As a timekeeper, I will notify the speaker if the remaining time is around 5 minutes. The second one, if any participants have any questions, you can do that by drop your question in the chat box down below available. I think that's it. Without further ado, I think we can start our presentation now. The first presenter is Dr. Sanjeev Kumar Panda from National University of Singapore. He's going to present single-phase inverter control techniques for interfacing renewable energy sources with microgrid parallel connected inverter topologies with active and reactive power flow control with grid current shaping. Dr. Panda received his bachelor degree from South Gujarat University, India, master degree from Indian Institute of Technology, Banaras Hindu University, and the PhD from the University of Cambridge, UK in 1991, all in electrical engineering. Since 1992, he has been holding a faculty position in the Department of Electrical and Computer Engineering, National University of Singapore, currently serving as Associate Professor and Director of the Power and Energy Research Area. Dr. Panda has published more than 450 research papers, co-authored several books and book chapters, holding 6 patents and co-founder of 3 startup companies. His research interests include high performance control of motor drive and power electronic converters, conditional monitoring, and predictive maintenance, building energy efficiency enhancement. He is serving as associate editor of several IEEE transactions. He is the chair of IEEE PELS Technical Committee. Dr. Panda has been very active member of IEEE and currently is a senior member of IEEE. Please welcome our first presenter, Dr. Panda. So, sir, if you all set, screen is yours now.
Thank you. Thank you and good morning to everybody. My name is Sanjeev Pandey from the National University of Singapore. Let me share my slide. Alright, is my slide visible to everybody? Okay. Am I audible clearly?
Yes, sir. Yeah.
Alright, thank you. Thank you for inviting me to give a keynote presentation on this topic of power electronics and power converter in the smart grid area. Before I start my presentation, let me introduce you briefly the National University of Singapore and few slides to give a background about NUS. So, the National University of Singapore is one of the few universities. There are about 6 universities in Singapore now, but this is the premier institution started long back, and is more comprehensive university starting with medicine to engineering to law to management, science, everything, arts and social sciences. So I come from the Faculty of Engineering, which has about 8 different departments, and I'll give an overview of the Faculty of Engineering. So the faculty profile, if you look at it here, we have in the Faculty of Engineering itself close to about 6,000 undergraduate students, about 3,000 postgraduate students, and 17 or 1,800 master students and about 1,000 PhD students. That's the student population. Then we have the staff strength, about 350 academic staff, close to about 900 research staff, support staff, and the adjunct staff over here. So as I said, the Faculty of Engineering has 8 academic departments, and there are 10 different undergraduate BEng program. We offer about 15 MSc program and 8 joint PhD program. And ranking wise, I don't need to go details of it. Many of you know NUS ranking. As a university, NUS is in the top 25, and in the Faculty of Engineering, we have several departments out of the 8 who are in the top 10 ranking. And my own department, Electrical and Computer Engineering, is somewhere hovering around 6, 5 or 7 typically. So, undergraduate student, as I said, 6,000, graduate student about 3,000 or 2,800, faculty member about 340, research staff 1,000, and lab and admin support about 300. So BH 10 different program, and it is a full-time program of 4-year duration, starting from first year to the 4th year. Graduate degree program we offer 2 types. One is by coursework, which we call as Master of Science. Full-time typically takes about 1.5 to 2 years. And most of the students are part-time student, working engineers. They come back in the evening, and they take roughly about 2.5 to 4 years. And by research, we have 2 different programs, Master of Engineering and PhD. So by and large, most of the students join for the PhD, because after bachelor's, somebody can join PhD straight away, bypassing the MNG. But some people, they want to do masters only for 2 years, then they join MNG degree. But the scholarships are given only for PhD, not for the master's program. So the mission and the vision statement goes like this. So the vision statement is a great engineering school that innovates for a better future. And the mission statement, if I may read, to nurture holistic engineer to address the global challenges by doing research, innovation, inspiring people, and influence the community to achieve our mission. Undergraduate program, the 8 different programs, as I said, there are different departments: biomedical engineering, chemical, civil. Computer engineering is a program, but the computer engineering and the electrical engineering degree program are jointly offered by our department, electrical and computer engineering. And the other programs are industrial system engineering, material science, mechanical engineering, and the list goes on from there. Research-based program, according to the department, biomedical engineering, chemical and biomolecular engineering, and electrical and computer engineering, where I come from. Material science, mechanical engineering, industrial systems engineering, and management is the other type of PhD or MNG program we offer. These are the research-based ones. MSc course, there are 15 different, and my involvement is in the electrical engineering degree program at the MSc level, and I teach modules in power electronics, smart grid technology, as well as electric drives. So the building blocks for research excellence, so we impact on research, but in the recent past, rather than doing just academic research, we try to make a balance between academic and translational research. So some of our PhD work can be translated into product. So the National University of Singapore has come up with a new program called GRID, Graduate Innovation Research Program, which is more translational side of it. So the students are encouraged to have a startup company towards the end of their PhD degree if their research work is leading towards a product that can be commercialized. So we do talented and faculty students. State-of-the-art facilities are provided in our research lab, and peak of excellence we have in certain key categories that we have. And as I said, societal impact, which is the balance between academic and translational research, has been gaining momentum in the last couple of years. These are the different research areas of peak of excellence: urban solutions and sustainability. So your smart grid could be a part of this one. We work in the domain of marine and offshore, and energy, of course, for the smart grid, and the list goes on from here to the other area. So my research is involved in the marine offshore, USS, energy, some part of robotics, the next generation of port and satellite for power supply design, and hybrid integrated flexible electronic system. I don't work in that domain, but on the outskirts of that one, Internet of Things, where we use this type of devices. So that gives the background about the Faculty of Engineering and the Department of Electrical and Computer Engineering, where I come from. Next, I move on to the research in my lab, the Electrical Machines and Drives lab, which is what I'll be talking about now. Let me give an overview of the responsive grids for future energy systems. So if you look at it, the focus area is energy system intelligence and management, energy system design and optimization, power distribution systems, and electronics. How electronics and power electronics is becoming a part in the distribution network. That is what we are interfacing at the boundary between the two. Responsive utility grid, responsive microgrid, and in a smaller scale, we have been working on responsive building grids. So each building, high-rise building, can itself be considered as a building grid or nano grid. So from nano grid, you go to the microgrid, couple of buildings in a cluster, and a couple of microgrid in a clusters can be connected to the utility grid. And grid edge GIS integration, that is one part of it, so that you have visualization of the whole grid from your command and control station. The challenge that we have is in mitigating the carbon emission, and we call it in the grid 2.0. So Singapore Energy Market Authority has defined the grid 2.0, which is the future grid that is going to come, and the present grid, conventional grid, is grid 1.0. And how smart grid would be a part of the grid 2.0, that is what we are aiming towards. Now, on this diagram, what you see on the left-hand side, you see the total electricity generation in gigawatt hour from Singapore point of view, or from Singapore. X-axis is the time scale from 2012 to 2020, and on the other side of the axis is the emission rate, that is called grid emission factor. The unit for this one is by consuming a certain amount of electricity, electrical energy, how many kg of CO2 per kilowatt hour are being released to the environment, and that is polluting the environment. So we know that the energy consumption is keep on increasing in a linear rate, which is not good. It should be tapering up and then start to decline. We haven't reached up to that particular point. So in order to maintain our standard of living in the city-state country, we consume significant amount of energy, and that is why you see the energy consumption is growing up. But at the same time, from 2012, the grid emission factor is dropping from 0.4772 to somewhere about 0.42. And this is in 2016, the data that I had. Now, how come when the energy consumption is increasing, how can the grid emission factor is dropping? That is only possible by using, we are still using fossil fuel, which is the natural gas. And that is the most cleanest form of fossil fuel that we could use to produce electricity. And almost 97% of the electricity generated in Singapore are from natural gas. That is so. If we use to reduce the grid emission factor further, if you make it 100% natural gas, then also this dotted line or dashed line that you see, that is the factual barrier. Even if you make 100% natural gas, cleanest form of the fossil fuel, you cannot reduce the grid emission factor below 0.41. So how do you solve this particular problem? So the grid emission factor can only be reduced if we make use of renewable energy sources. Renewable energy sources such as photovoltaic and wind power. But Singapore being very close to the equator, we have only facility available is the photovoltaic generation. And the more we bring in renewable energy source into the energy mix, we can reduce the grid emission factor even further down. So that requires a paradigm shift in the grid structure. So the conventional grids are, you have a generation and at the point of the common coupling, your demand. So the power flows or the energy flows from the generation to the demand in one way. That is the conventional grid what we have now. But increasing complexity can be managed in where you have a conventional generation in grid 2.0, but we have a responsive local generation like renewables 1, renewable 2, energy storage devices. So this dotted, the rectangular box with the dotted line, that is the distributed generation that we can do it. And we also want the demand to be responsive rather than passive. If the demand can be modulated depending on the generation, then you can match the generation with the demand and power flow would be maintained and resiliency can be maintained. So this is what from the conventional grid you are going into the microgrid, and the other speaker yesterday must have talked about this thing. The challenge is temporal, spatial and structural variation when you are using PV. So this top graph shows you from January to October the mean output power in kilowatt from the PV generation, roughly about 200 kilowatt. But this is fluctuating, this is not fixed. So power dispatch cannot be done, and that brings in the difficulty there. So this is the Changi airport. So we have terminal 1, 2, 3, already T4 is there. Now if you look at it on the right hand side, there is a cloud, white color cloud over there, and the shadow of the cloud is falling on the ground. And if you have solar panel over there, this shadow will be reducing your power producing capability during that period. So when there are shadows and the clouds come in and go out, at that particular point, our power generation from the solar photovoltaic will dip. So unless you have mechanism to supply that power from other sources, be it a energy storage device or be it a generator pumping in more power to meet the load demand, the grid may go into instability. So these are the challenges that we need to do. So time varying, spatially varying, and variation in structure. The distributed power generation, renewable 1, 2, 3 can come in, can come out. So they call it the plug-in or plug-out type of system. And that is one of the drawbacks we have to solve. So higher responsive to match the higher uncertainty, you need to basically predict how the load is going to vary, how much of power generation can be done under different climatic conditions. So higher flexibility to quickly respond, that depends on, you depend less on your forecast. So how much of solar will be there, how much of wind will be there. You may go wrong in your forecast, but if you less dependent on the forecast and act in real time, then that will be much better. So we want to minimize the spinning reserve, so lesser energy is wasted, lesser emissions will be there. And all these things can be done if you can take faster decision and faster optimization and smaller battery installation to overcome the instability in the grid. And these are the research challenges that we have and we need to solve. Yeah, just give me a minute. This diagram that you see this is bright sunny over there. In the next few seconds, the whole island, Jurong Island, that's been covered with cloud. And that is one of the drawbacks. Unlike in the Middle East, you do not get a clear sunshine all the time. Clouds come in, clouds go out, and they create the variation in the power generation. So this shows you the real-time power flow management. G is the generation, the green color PV is the photovoltaic, the blue color is the demand, and the pink color is the ES. So, if I may, yeah. So this shows you the animation how in grid 2.0 you have a conventional generation, you have distributed generation, and each machines are intelligently, all are connected and they're intelligently controlled so that the system is in stable form. That's the research part of it. So that gives you a background of the research that we, or the challenges that we have in the microgrid. So now I'll go only one part of the power converter, how a sophisticated intelligent power converter can be designed for microgrid application. And for this particular topic, I would like to say that this is one of my former PhD student work, so I have taken part of his work and presenting on behalf of him. So a typical multi-bus microgrid system looks like this one. So at the top you have the utility grid, then you may have some loads connected there, then you have an isolating transformer over there, then you have a static transfer switch. So this is just like a switch. A switch can be closed, then it is grid connected. If the switch is open, then the microgrid is isolated. So then you have a common bus over here, and then you have a red color rectangular block here, which is called DG1. Then we have this green color box here, which is the distributed generation 2, DG2, similarly DG3. That could be multiple microgrids or multiple distributed generations all connected in the form of a microgrid. So the dashed line that you see, rectangular box, that is a microgrid. A microgrid can be grid connected or can be isolated. Okay, so the main challenges that we need to solve for this one, I'm just focusing only on the DG1, where I have a renewable energy source, I may have an energy storage device, and they are connected through the inverter to the local bus, and the local bus is connected to the common bus, and the common bus is connected to the utility grid, like that way. So this particular part, the inverter that connects the renewable energy source to the local bus or the utility grid, that is what we will be discussing now. Yeah, so that inverter requirement will be high bandwidth active and reactive power flow control, total harmonic distortion control of the current drawn from the AC bus, either drawn or injecting into the AC bus, how you minimize the harmonic distortion, load voltage regulation that we need to do. And the static transfer switch STS, as I said, can be turned on or off to make it grid connected or isolated. And DG1, DG2, DG3 can be fossil fuel based power generation, or it could be a renewable energy source. So DG2 is a fossil fuel based diesel generator. Now, I'm talking about single phase supply here. So on the left hand side here, you see all the typical, give me a minute. Yeah. All the renewable energy sources are here. So the renewable energy extractor extracts the maximum power from the renewable energy sources. And then you have the power and power electronic converter to ensure that the MPPT is being done and you are extracting the maximum power. Then you may have a storage or a battery that is, or a capacitor that is the DC link voltage. And that DC link voltage is connected to the inverter that you see it here within the rectangular block here. So it is a single phase H-bridge inverter, and the output of the inverter are connected through the line impedance across the grid. So this is your grid and this is your load. So the requirement are that the load needs a certain amount of active and reactive power, PL plus JQL, that can come from the grid. So the grid can give you PG plus JQG, and the renewable energy source can provide you P inverter plus JQ inverter. So if I do the comparison, PL, active power of the load, can come from grid or can come from P inverter, and that is how we got this particular equation. I'm assuming that the reactive power requirement is 0 and we operate with a displacement power factor of unit. Now this inverter must provide a current IC, and how I control the inverter to provide this current IC. So IC at this particular node, IC plus IG will be equal to IL, and that is what we need a nonlinear current controller to control the active power flow and the total control of the grid current. That is what we will be discussing now. I'm not going through the mathematical part of it, but the slides will be provided to you. So basically, if you look at it, you have the DC voltage source here, the inverter, that is pumping in the current IC, and the grid will provide you the current IG. So IG plus IC becomes IL. I'm assuming here that I know how much is the load power P and Q, and I can monitor the grid voltage VG. So I know VGR and VGI. Knowing this information, I can come up with the reference grid current IG. If I know the load current measurement and the grid current from calculation or based on P and Q requirement of the load, then I can subtract IL minus IG will be equal to IC, and that is what IC is IL minus IG. If I know the load current, I know active power P and Q and the grid voltage, I can calculate the reference current, the inverter, and control the inverter to give that particular current IC. Yeah. So IL minus IG will be equal to IC. Once you know this reference current, then you need to control the inverter accordingly. So I have a simplified nonlinear controller and simplified the current control voltage source inverter that I have, and I have the grid over here, and the inverter and the grid are connected through this particular. So if I write down the voltage equation here, your dx, basically dic by dt is given by this, which is the grid voltage and the inverter voltage Vc. Then I can write down in the nonlinear form x dot is equal to fx plus bx u plus d. So I need to calculate what is this control signal u, and that is shown over here. I use the Lyapunov function based controller to track IC, and error is the desired state variable, which is IC star minus IC, and I try to minimize this error by choosing the control signal to be this form. So this is the control loop, reference current, current measured, and error signal. Error signal is processed through the nonlinear Lyapunov function based control, and that gives me one control voltage ULF, and another spatial repetitive control gives me another control to compensate for the disturbances, periodic disturbance in the system. Then that becomes your control signal, and you limiter and assign PWM scheme to give the gating signal to the single phase inverter, which is operating in current control voltage source inverter mode. So I take two examples and then I'll be closing my presentation. So this is the experimental result. Now my requirement is I have a active power requirement of 30 watt, 35 watt, and my grid voltage in the lab environment is 50 volt from a programmable power supply. Now I assume in this particular test that my inverter is sufficient enough to meet the load power demand PL. So if the inverter from renewable energy source is able to supply the total demand, I don't need to draw anything from the grid. So the power drawn from the grid is 0. And that is why your Ig is 0. This is my grid voltage, Vg, which is perfectly sinusoidal. And my load is a rectifier load which is highly nonlinear. So the load current is given by here. You can see it is not sinusoidal and it is highly nonlinear in nature. And the total load current comes from IC plus Ig. Since Ig is equal to 0, IC provides the total load current. So you can compare the inverter current is almost close to that of the load current. And Ig is very close to 0 except some disturbance over there. So the total current drawn from the grid is 0. I can achieve it. Now I go back to the second graph over here. There is a problem here. Because of the cloud or something, the inverter cannot give you more than 5 watt. But the load power is still 35 watt. So 35 minus 5, 30 watt must be drawn from the grid. And when I try to draw from the grid, the supply or the control signals are here. So the grid voltage is the same as that of this case. The load current is the same as in the previous case. But the grid current which was 0 here, now I have a grid current which is different than the previous case. So the grid current plus the inverter current is different compared to this one. So grid current plus inverter current becomes the load current. And you see the inverter type of current IC, that is highly nonlinear. And therefore a simple PI control cannot do the job. And we take a nonlinear current, rather nonlinear controller, Lyapunov function based control, and we only draw the fundamental component of the current of the active power 30 watt from the utility supply. So you see this 0 crossover of the current and the 0 crossover of the grid voltage, they are matching. So the current and the voltage are in phase and we draw 0 reactive power from the grid side. And looking at the shape of the current, you can see that it doesn't have harmonics. It is just the fundamental component of the current. So this gives you the steady state characteristics. This I skip it. And this gives me the transient characteristics of the supply. So until this particular point, it was operating. So that is a transient phenomena taking place here, and a zoomed view of that is shown over here. Now, until this particular time, the power drawn from the grid was 10 watt, reactive power was 0, and at this point I give the command to increase the power drawn from the grid from 10 watt to 30 watt. So this is a transient response. So how the grid current from here increases to this one. And the system is quite stable, load current is highly nonlinear, and the system stabilizes properly. So transient response is also equally good. Okay. So to summarize, the proposed single-phase PQ theory-based approach ensures easy control on the grid active and reactive power flow. Remember that it is a single-phase system. PQ normally happens in 3-phase systems, but we have applied the single-phase PQ theory for single-phase system. That's the unique novelty of this particular part. And because the current reference is highly nonlinear, we propose a Lyapunov function-based current controller that is simpler compared to the DQ frame PI controller plus the multiple proportional resonant controller. So for different harmonics, you will have several PR resonant control. That makes it more complex. Here we have just one nonlinear control able to do the job. And the proposed controller provides better tracking, enabling single inverter doing both power flow and power factor correction. Remember that there is no controller between the grid and the load. It is only the renewable energy side converter or inverter is able to manipulate the grid current in an intelligent way because the intelligence has been implemented in controlling the grid side inverter. I guess I'm on time with my 30-minute presentation. Dr. Ali hasn't given me the warning, so with that, I think I thank you for your attention, and I'll be more than happy to answer any questions that you may have.
Okay, thank you very much, Professor Padan, for your very interesting presentation. Now it's time to Q&A session. We're going to have around 10 minutes for this. If anybody has a question, can drop your question down below. Don't forget to mention your name, identify yourself, your affiliation. And I think we have the first one. The question is coming from Dr. Moni. So the question is, how do you think about the Sun Cable project? Will it have negative impact for the grid in Singapore due to the uncertainty of the sources?
I believe Sun Cable project, you are referring to the power being transported from Darwin in Australia through cable connection into Singapore. If that's the case, I don't think that will have any major impact because our energy consumption is increasing, and in the energy mix of Singapore demand, at this point, the renewables are only about 400 megawatt or of that order. But the target by 2030 is to go to 2 gigawatt peak. So Singapore doesn't have that much of land to produce electricity from renewable energy source. So in the ASEAN grid meeting, what had been discussed recently is to interconnect the grid. So Singapore is connected to Malaysia at this point of time. Malaysia is probably connected to other countries. So we look at Laos and other parts of the world within the ASEAN region where it is possible to produce renewable energy source based electricity and connect to the grid, and Singapore will be buying the green electron and be more responsible towards the utility grid. That is one way. But the future of the transportation sector is based on hydrogen economy in the long term, not in the near term. So how do you produce hydrogen from green source that is using renewable rather than using fossil fuel based? That is what is the point. And in that context, where Australia has significant amount of land space and sunshine, so if you produce renewable and transfer it back to Singapore and we consume that for shipping, for transportation, land-based, everything, EV, then that would be a major demand, and that is why the government is looking at it.
Okay, thank you very much. Are there more questions from the floor? So while waiting for the more questions, I think I have a question. What is the percentage of energy coming from renewable energy resources in Singapore?
Our demand is about 8 gigawatt at present, out of which it is just merely 400 megawatt. So it is very, very small at this point of time. But the plan is to increase that 400 megawatt by 2030 to 2 gigawatt. So if it goes to 2 gigawatt out of 8, roughly, it will be about 25% of coming from the renewable.
So is that probably the future? Do you think it's going to have? Do you think Singapore going to have like problem with virtual inertia that's now the European and American countries facing, as more and more renewable energy penetrating the grid? Do you expect the same problem?
Yeah, we do have, yeah, there will be, because these are not traditional synchronous machine type of generator, so the inertia is not there. So if suddenly there is a active power demand goes up, then at that particular point the system may become unstable. Now, what we are also researching on, and I have a project funded through Energy Market Authority, is to develop a floating living lab. So on the floating living lab for Keppel organization, it has a gas turbine, 2 of the gas turbine, it has a solar panel, and it has a 1 megawatt hour energy storage device. All these floating lab power systems are being developed for the harbor crafts for marine domain. But it is also connected to the land-based system, utility grid. So when there is not enough demand and you need to stabilize the system, then this type of energy storage device connected to the grid would be able to inject active reactive power to stabilize the system. So Singapore is going, this is one project. Another project is the Port of Singapore Authority PSA. They also have planned to develop a floating living lab on the seabed, rather on the seawater, and have the solar panel on the sea, because we don't have that much of land space. So by integrating this type of energy storage devices distributed way and having power electronic controller, you can react in milliseconds to stabilize the whole system. So you think about Denmark. How come Denmark? People say that, oh, if you go more than 20% or 30% of renewable in the grid, then system may collapse. But Denmark is already close to 70%, and they are stable. Of course, they are connected to the European grid, so they have a larger inertia. So same way, in ASEAN countries, my feeling is that it should be the ASEAN grid connected, so you have a larger inertia there, and you can then draw power from the other country in an intelligent way, and if it is controlled properly, then system could still be stable.
Okay, thank you very much. I think it's going to be the last question. Is it possible to stabilize the system which has functioned as free government, as a follower power plant?
Is it possible to stabilize the system which function as free governor? I'm not getting the question clearly. Could you rephrase?
Probably if we have a generator that has a functioned, set the governor as a follower of the load, is it possible to stabilize the system in that case?
As I said, if you have energy storage device and power converter, then suddenly load comes in or load goes out, then the systems become quite stable if your controller is fast enough to pump in the active or the reactive power to stabilize the system. And with energy storage device and power electronic controller, yes, it is possible to do that. And if the disturbance stays for a longer period of time, you can turn on a gas turbine within a matter of 10 minutes or 15 minutes to supplement the power generation, because the energy storage, you cannot have infinite time to discharge from the battery. But with limited energy storage device and backup generator to quickly start it, then the system can be stabilized.
Okay, yeah, I think so, yeah. I think, do you think we need to, this is the last question, do you want to, so it's coming,
I saw it.
Yeah.
The inverter and energy storage play an important role in the grid due to uncertainties both demand and generated from the PV. Agree. The research is interesting in controlling the current IC. Can this model be generalized for other types of renewable energy? Yes, that is why the renewable energy source side, if you look at it, I saw not only photovoltaic, hydrogen fuel cell, or even wind, any type of renewable energy source at the source side, and you have MPP. So this methodology to control the active and the reactive power flow is universal. It is independent of what type of renewable energy source you have. And this is, I just showed you only for the parallel connected. But the problem with the parallel connected inverter is that if the grid is corrupted, your load connected in parallel with the grid will see the corrupted voltage. You get my point? But then, how do if my load is sensitive, and it cannot take any corrupted harmonics in the grid voltage, how do I clean it up? So you can use UPS, things like that. But I have another part of the research which I'm not presenting here, is if the grid and the renewable energy source are connected in series, the grid has harmonics, I can inject the anti-harmonic part from my renewable energy source based inverter to compensate so that the load sees a perfect sinusoidal voltage. So that is called series connected inverter. If you Google my name, we have publication in the Power Electronics Transaction for series connected inverter, but because of the time limit 30 minutes, I did present that particular part of the research.
Okay, I think probably some participants still have more questions, but I think time doesn't permit us to continue. So if any one of you has a question, you can probably drop email to Dr. Panda.
I will provide a copy of the slide so you can give it to your participants. Then they can refer to it also.
Okay, thank you very much. So,
okay, thank you very much for inviting me.
Yeah, thank you very much to Dr. Panda for a very interesting presentation. Thank you very much.
Thank you.
I think it's now time for our second presenter. For this, we're going to have Professor Ankush Bose from Nyotia University, India. Are you present now, Professor Ankush Bose?
Yes, Dr. Ali.
So, the title of his presentation is Artificial Intelligence for Future Generation Robotics. Professor Ankush Bose is senior member of IEEE, fellow of IETE, currently working as associate professor and head School of Engineering and Applied Sciences, the Nyotia University in India. He received his PhD degree from Jadavpur University, India in 2010. He has outstanding research experiences, published books, patents, and more than 100 research papers. He is serving as an editorial board member for several international journals. He has more than 15 years experience in teaching, research, as well as industry. Please join me to welcome Professor Bose. So, sir, if you all set, I think time is yours.
Okay, thank you, Professor Ali. Sir, I have one correction. Actually, the presentations I have sent and I have also shared to you that applications of AI and IoT in renewable energy.
Okay.
That was the top title.
That's okay.
So
Yeah.
there may be some miscommunication.
Yeah. I think the old one. So my apologies for that.
Sir, is it, sir, visible?
Yes, visible. Yeah.
So I'm making it full screen mode.
Yeah, it's perfect now.
Is it changing? The slides are changing?
Yeah, the slide is changing perfectly.
Okay, fine. Thank you very much, Professor Ali. In this lecture, I'll be going to explain about the applications of AI and IoT in renewable energy. just a minute. Yeah, in renewable energy applications. So basically, in this lecture, I'll be providing I'll be explaining some of our work that we were doing for the last few years on the renewable energy applications. So here in these today's talk, I'll explain about the applications of different AI and IoT applications in the renewable energy applications, where we have published two books on these particular area, one from Elsevier publications, one from Springer publications, where these two books are edited books where most of the contributions from our side, from our PhD students and our research. So let us see the outline of this talk. So basically, we'll start with some background of these AI and IoT in the renewable energy area. Then I'll discuss about some of the case studies and what we have done. So in these particular talk, I have included 4 different applications of AI and ML. 3 different applications of AI and ML in renewable energy applications, and 1 IoT applications in renewable energy area, and their challenges as well as future scopes. So first we'll start with applications of AI and ML in temperature and weather-based power generation for forecasting in PV system. Then we'll discuss about the tidal, how AI and ML can be used for tidal applications, tidal renewable energy conversion system. Then we'll see how these AI and ML can be used for the hybrid renewable energy system, and finally we'll see how IoT can be applicable in renewable energy generation system. So let's start with the background. We know this is very common. Basically, all of us, we know that these renewable energy nowadays are very important. In our for our environment as well as for our system, due to these ever increasing energy requirement of worldwide, which cannot be compensated with conventional energy resources. And also conventional energy resources, we know, are limited and it is under depletion. So therefore, in very near future, we have to convert to these renewable energy sources. And also these renewable energy resources has one of the most major advantage, that is it is hazardous free. It is very comfortable with the environment. So therefore, that is also one of the major reasons to choose about the renewable energy. And so therefore, basically, in these renewable energy resources we are using is solar energy, wind energy, and hydroelectric energy. As we know, also in biomass energies in some cases. So that is why we are basically taking these. We are basically most of our focus is on the solar energy resources, and how the solar energy resources can be optimized. And these optimization techniques are going on for last few decades. That people are researching on optimization of the solar energy, and so that we can get the maximum energy out of it, maximum efficiency out of it. So So therefore, however, these optimizations techniques are outdated now because of the advancement of artificial intelligence and machine learning nowadays. Because since last few years we have seen there was a huge development of in the artificial intelligence and IoT sectors because of development of hardware in recent times. So therefore, that becomes our job easier to go into these artificial intelligence and IoT applications if we can apply these recent advancement of artificial intelligence and machine learning into these renewable energy applications. So that will make our system more optimized and more efficient than the conventional optimized based system. So that is the main reason for doing research in this area, and therefore that is the reason we are doing research on this area, and we have applied this artificial intelligence, machine learning, as well as IoT, that is Internet of Things, in these renewable energy based power generation system. So the first applications or case studies I have shown here, that is applications of artificial intelligence and machine learning in short-term PV solar irradiation system, and it is used for temperature forecasting at the microgrid. So basically, we know that we are discussing that we are applying this artificial intelligence and machine learning approach in these PV system to get optimized, to get a better efficient system. So one of these applications we are giving here to forecast the solar radiation as well as temperature. So for these we have applied different AI/ML model, and starting from artificial ANN to artificial neural network to linear regression, to random forest regression, RFR to k-nearest neighbor k-mean algorithm to support vector mechanisms SVM. So different. Basically, we know in those who are working in artificial intelligence and machine learning area, there are different algorithms are available for these optimizations, and generally we are applying different different algorithms to get the maximum efficiency, and then finally we will compare these different models, and we'll see from which algorithm we are getting the best efficiency, and that can be selected for the applications. So this is the prediction methodology that we are taking here for these artificial intelligence algorithm applying. So for solar irradiance, we know solar irradiance is the power that we are getting from the sun. So to optimize the solar irradiance, we are taking temperature, solar flux, humidity, pressure, and wind speed as the parameters for these AI-based algorithms. Then the solar irradiance is converted into the solar energy by solar panels, and to optimize this solar panel, we are taking parameters as the duration of solar energy, the solar irradiance, the generation, as well as history. history means the time history, how much it may be in last few months or few years, so like that. And then this solar energy is sent to this load, and in calculation of these load, to optimize this load, we are taking the parameters duration and load history for that calculations. So these are some of the prediction methods. We have given some examples. Artificial intelligence is mostly used for these AI, that is artificial intelligence based optimization, and we know here this is a very simple algorithm used here. These input layers are there. There are neurons in the artificial neural network, and these input layers are, the inputs are like if you see these x1, x2 up to xi inputs can be fed, and these are called the weights. W1, W2 up to Wi can be the weight, and therefore the summation will be equal to x1 W1 plus x2 W2 up to xi Wi, which will get the summations, which is to multiply with the activation function to get the output. Therefore, it is activation function is the most significant portion function in these calculations, and it is basically depends on these activation functions. So these can be a simple neural network like this. There is some hidden layers are there, and this can also be a multi-layer artificial intelligence network where the number of inputs as well as the number of weights are as well as the hidden layers are higher than one. So next, coming to the data description, as for this forecasting model, the solar irradiance input data, as we have just discussed, that the input parameters should be maybe like temperature, wind speed, humidity, pressure, wind directions, as well as solar flux. And for solar energy, the input parameters maybe the durations, solar irradiance, generation history, and for load it should be a duration as well as load history. Then coming to the prediction term, so these prediction term can be divided and in three types, like it may be short-term prediction, it may be medium-term prediction, or it may be long-term prediction. So the short-term prediction may be less than 30 minutes, and in some researchers they are defining these short-term from 1 minute to a few hours. And in case of medium term, we can define it from 6 to 12 hours, maybe 1 day, or maybe 1 week and 1 month. So, and for the long term, it is starting from 24 hours to month, and maybe a year we can predict. So these are the one sample data set that we have shown here, that can be taken from any PV generation system, and this data set, this temperature humidity data set, is we have seen one of the parameters for this optimization. And here we have shown validation and training sample of these solar irradiance forecasting, where we can show. We have shown here some errors during the training, how much error that can be possible during the training as well as during the forecasting validations. And now finally, after applying these artificial intelligence algorithm, if we predict it, and if we see how what is the convergence rate of our prediction system as well as our actual system, and we'll see it is almost similar, the prediction that we have received from the calculation, it is almost similar, and therefore in some cases it is very minute deviations are can be seen here. And this is the results of a few different algorithms other than ANN. Here we have applied the LR algorithm. Here we have applied the KNN algorithm, the K-near estimable algorithm, and this is the result that is shown here. And similarly, we have applied another one more algorithm, that is SBM algorithm here. Now this is the actual data of solar irradiance outside the PV panel, and this is the actual data of temperature outside the PV panel. So that is shown here. And finally, as we have said, for all of these type of work, these artificial intelligence or machine learning work, or it may be higher, that is deep learning work, we are basically using different algorithms, and then finally we'll see the comparisons. And here we have given the advantages and disadvantages of different algorithm. You have seen for ANN algorithm there are advantages, like it can handle a huge data, and it has the ability to work with the incomplete data even. However, it has disadvantages, like it needs a huge time to process, it requires high performance hardware. And for the KNN algorithm, it is also for the for forecasting the short term duration, and it is very easy to implement, and it do not need any learn from the training. And it has disadvantages, like it doesn't work with large data set, and also it has a disadvantage of scaling up. It needs scaling of the parameters for applications. And then coming into the RF algorithms, it is also a short-term forecasting algorithm. It can be used for it is very easy to use, and it can be used to solve the classification problem. However, it has disadvantages, like it is very complex to implement, and it requires huge training. Next, coming to these RNN algorithm, and so it is also used for short-term forecasting, and it has advantages, like it has a powerful time series predictor. However, it has disadvantages, like slow computation, like training data can be difficult. So this type of disadvantages are also there. And finally, for SVM algorithm, it is also used for short-term forecasting. It has problem like overfitting is less in case of SVM algorithm, and it can also be used for unknowledge data set, and it is very easier to implement. However, it needs a long training time, and it can get difficult for tuning the hyperparameters. So these are the advantages and disadvantages of these various uh, techniques for artificial intelligence and machine learning. Now coming to the comparison of forecast of solar irradiance in daily time, we have see how it differs from the actual data that here different algorithms are used like random forest, Euler, KNN and SVM algorithms we have used, and which is convert with actual data, and this is what we see how it differs from the actual data with timing. So this is morning at 6, at 12, and at 6 at the evening. So now next is we are as we have predicted the temperature based forecasting. Now it is weather based forecasting prediction. So here for weather based predictions, we need to input the weather features and there may be some input defense layer, input dense layer, and it moves to output dense layer, and finally linear activations, and from which we are getting the power generation activations. So this is applied the linear neural network for regressions, where these regressions equations square is can be found from these equations. So, which is the residual sum of squares. So this is the sample data set that we have used here to calculate the predictions, and this is the predictions that we have received from the algorithm calculations, that power generation, actual power generation, and predicted value you can see almost converge here. So this is the correlation model that we have shown here for different parameters. The correlation matrix are plotted against different parameters like ambient temperature, like irradiations, like AC power, like daily yield. So these are the different parameters that we have taken and plotted the correlation matrix here to see the rate of convergence. So so these two were the PV applications. Now we are moving into these. Now we are moving into these tidal power system. How AI and ML can be used in synchronous generation in tidal renewable power system, that conversion system that we see here. These are the simple model of tidal conversion system, where tidal turbine is here and back converter is there, which the power is flown through this system, and finally from the transformer it goes to the grid. So this is the tidal current model, where the captured mechanical power Pn is calculated like this, and from here we can calculate the tidal power from these equations. So this is the model for PMSG model, that is permanent magnet synchronous generator model for tidal power generation system, where here in this particular case we have used a fuzzy controller to optimize the system, and from which we are getting these output here in these from these PWM inverter here. So next is the desired torque computations. How we can compute these our exact torque of these tidal power generation system. So here also we have used that because, as we have said, we have used fuzzy controller system to get the optimizations of tidal power generators. So this is the simple systems by which we can get our desired power. You have seen there is a feedback system by which we can optimize, or we can get our desired torque computation from this tidal power. So this is the membership function of the speed error as well as the speed variation, and the membership function of the output of fuzzy controller that is shown here. So this is the this is made from the MATLAB plotting of fuzzy controller configurations for these particular model that we have developed and shown in earlier slide. And so finally we have received the result of tidal speed and electromagnetic torque response shown here, and the DC bus voltage shown here, and zoom of these, we have zoomed these DC voltage, and which is shown in this particular plot. Here we have plotted the active and reactive power with time, and zoom of reactive power is shown in the next plot, and the grid injected voltage is shown here in this particular plot. So as we have said, we'll show the four applications of AI and ML in renewable energy sector. So we have seen in the last three applications where temperature and irradiance are predicted using AI/ML. Then in the last applications we have seen how we can predict the tidal power using these AI/ML systems. There we have applied the fuzzy controller, fuzzy logic systems. And finally, in these applications of PV system, here we have used AI and ML applications for hybrid renewable energy system. So hybrid renewable energy system means that there may be PV source as well as maybe some other source of renewable energy. So here we can see this is the simple architecture model of hybrid system that we have taken. Here PV source we have taken for DC to DC converter which goes to load, and as well as we have taken another system that is wind generator system, and here also is a DC converter which goes to load, and load may goes to battery or in during the off time battery may again uh, fed to load. So that is the total simple architectures of these hybrid renewable power generation system. So next I'm coming to these conventional dropping characteristics, where we have shown these the grid impedance P and the Q power overflow is shown here in these two particular characteristics, where P is equal to this and Q is equal to these equations. I'm not going to explain these equations here. So the control strategy for these yes, so we have 5 minutes more. I'll try to sum up as early as possible. So in the control strategy that for these hybrid power generation system, here that can be calculated like this, delta P, delta A, and finally here like this. So the parameters of hybrid system that we have taken here, the solar thermal parameter, solar thermal source, wind source, field source, and diesel generator, and the gain and time constants are taken as the parameter for these calculations. And this is the simple neural network model, as we have already discussed, that this is the hidden layer from which we get the output. So this is the finally simulation results. You can see how the performance of these hybrid power generation system using artificial intelligence. And this is the error function behavior that is shown here, the error histogram. And next, finally, we'll see the output power waveform of solar thermal and hybrid system with wind system and load damage. So this is from which we can compare the how our optimizations are done for different PV generation system. And finally, this is the comparative analysis of different parameters with proposed approach that we have developed, and that this is the conventional approach, and we have seen some improvement from the conventional approach to our proposed approach. Yes, so as we have only 5 minutes time, so finally we are moving to the final applications, last case studies, that is the applications of IoT in renewable energy generation system. So how IoT can be used in the renewable energy generation system. And here we have seen different IoT applications are there, because these AI, these artificial intelligence and machine learning algorithms who are performed, this has to be performed in a machines. And now the problem is that if we want to apply these applications of AI and ML in real-time system, that is very difficult to apply, because these PV generation system is somewhere else and we are working in somewhere else. So how to apply these AI and ML algorithm in real-time system, how to get the real-time data and how to manipulate these PV generation system in real time. So one of these solutions is the IoT, to apply the IoT, because if we can integrate these PV generation system, these tidal generation system, or any hybrid generation system with IoT. So what happened? These wind power, let us suppose this is the wind generation system, this is there may be some solar plant system, there may be some smart city grid. Those can be connected to these data center via IoT, where we can get the real-time data, and we can apply these AI and ML algorithm on these real-time data, and accordingly we can manipulate those parameters, some of the parameters of the solar plant or some of the parameters of the wind generation system, and therefore we can get the maximum efficiency out of these wind generation system or solar plant generation system. So that is the main applications of IoT in these particular applications of renewable power generation system. So here nowadays we are applying a new technique that is called fog computing for these particular solar or tidal power generation system, because this fog computing is basically the distributed computing. So for that the data need not to be reached to the cloud server system, because this fog computing is basically we can compute and we can keep the data in somewhere between cloud server and IoT devices. So which is basically required for this kind of these power generation system, for PV system and tidal power system. So yes, I'm trying to conclude within 1 minute. So therefore this fog computing system is very useful for these particular applications, and we have applied this fog computing system for these particular IoT applications. So this is the current state of digitalization of energy value chain. So I'm not going to explain these elaborately, just how energy generation and transmissions are happens, and how IoT can be applied in these power energy generation and energy transmission system. It is that maybe you can find from our book or our paper. So I'm going to explain basically these result analysis and discussions of different time slots, and we have seen these total energy consumptions with different algorithms is compared here. This leach, fuzzy leach, heat, and different hybrid algorithms are compared here. Here also various approaches are applied and compared with network lifetime. And this is the final comparison of transmission data with time durations that is shown in this particular plot. So finally, this is the reference that we have taken these applications. Basically, we have published 5 books in this particular area. For renewable energy, we have published 2 books, and for AI applications, other AI applications, data AI applications, we have published 3 more books from the Springer and the Sevier. And these 2 books you can find over net, that applications of AI and renewable energy. This has been published from Elsevier, and this is another book, this AI and IoT in renewable energy. These are the applications of AI and IoT in renewable energy, and this has been published from the Springer. So basically, I have taken some of the applications of from this book, and if you want to explore more, you can go through these books and find various applications of AI and IoT using these, for the renewable energy system. So that's all from my side. So if you have any questions, you can ask.
Okay, thank you very much, Professor Bas, for your excellent presentation on applications of artificial intelligence and machine learning on various aspects of power systems. It's time for question and answer. We have around 10 minutes for this. Are there any questions from the floor? Okay, question from
Yes.
Can you see?
Yes, yes, I found the question. In microgrid applications, the controller is usually placed in a microcontroller or single board computer that is low computation capability. How do you think AI ML method could be implemented in this microcontroller or SBC? Yes, this is a very valid questions. However, as we are just discussing, nowadays, in last few years, we have received huge development of hardware, and therefore the single board, even in the single board computer also, we can calculate these. We can use these AI and ML. Even we have seen some of the in Raspberry Pi also we can calculate these. We can use these AI ML algorithm. So therefore, in recent years, in recent hardware system, it is very much applicable that we can use these AI ML, and even in small microcontroller also Python codes are running. So therefore, this is very much applicable. Using these recent hardware, modern days hardware, you can use directly AI ML algorithm with this hardware. Also, we have another options. We can just use some IoT devices with these PV generator system, so that we can send the data directly to the cloud, and we can calculate we can use these AI ML algorithm in the server that is situated in the cloud, and from the server we can send the output to these PV system, so that PV system can work accordingly.
Okay, we have a second question from Ms. Swati. So beside the ML algorithm, what other things are able for us to note in generating energy from gas?
Yes, beside the ML algorithm, what are the other things important for us to know in energy forecast model? Basically, other than basically ML algorithm is not the important thing. Important thing is the parameters, that may be irradiation, that may be temperature, that is humidity. So these are the basically parameters that is we have to think of, and we are using these ML algorithm to optimize those parameters. So therefore, machine learning is not the important thing. The important thing is the parameters. We are not changing the parameters. We are just taking this parameter, and we are trying to optimize to get more efficient, better, more power, more energy. How we can generate more energy or more power out of these different parameters. So that is our aim. That is our objective.
Okay. The third question, very interesting. Can you have optimization algorithm that can be applied for real-time applications? Yes, then let's turn it to converge.
Yes, definitely. We can use these real-time applications, and we have already used. And if you see in the literature, they are used these AI/ML algorithm in real-time system, and that for that particular applications we actually need these IoT, because these IoT, using these IoT system, we can get the real-time data from the PV generation system, and we can calculate on these data, AI/ML calculations on these data in real time, and we can accordingly change we can try to change some parameters of PV generation system so that we can get the maximum efficiency.
Are there any more questions from the participants? So, according to your experience, what's actually the biggest obstacle to apply AI or ML algorithms to power system? Because if we see like robotics or medicine application, it's very huge there, but in power system, I would say it's still very limited. What is the main problem?
Major obstacle is that actually there is this is it should be two-way system, because we are optimizing to get better efficiency, right? So we are getting inputs from the real-time system. We are using AI/ML algorithm, and therefore the second part should be fed to the output. That means the PV generation system or power generation system, and the power generation system should be act like this. So, however, the problem is that whenever we are getting different value of the data of different parameters, and we are trying to get the maximum output. We have to change those parameters. Now the problem is that we cannot most of the cases we cannot change the parameters like angle of irradiation. So generally these PV panels are set in a particular angle. So to get the maximum efficiency, we need to change the inclination angle. So that will not be possible in most of the cases. We need to in some cases for the tidal power we can optimize to get the better efficiency. In that case we have to change the directions of that wind generation system. So that will also not be feasible in real life. So that is the most challenge. We are getting data, we are optimizing. However, the output cannot be applied in most of the cases.
I think we have one attendant raising his hand. Mr. Tom Market, are you willing to deliver your question directly.
Sir, yes, I would like to ask regarding the parameters of features used for the prediction. How did you choose the best feature for the prediction? Yes, that is a very valid question. That can be get from the theory. You have to see the dependence of of the your power generation system, and you will see which parameters is the maximum dependency for these particular power generation system. For PV system, if temperature would be the means if the power generation is maximum dependence on the temperatures, then you should take temperature the best features, right? If it is the irradiation, if you see the irradiation is the as per your calculation, irradiation is the maximum dependency on the efficiency, then you have to choose irradiance as the best feature for your predictions.
Okay, we have one hand raising. Pak Tom Nakin, do you want to ask something to Professor Bush? No, I think. Are there any more questions from the floor? Okay, if not, I think. So I think that's it. I would like to say thank you very much, Professor Bush, for your excellent presentation.
Thank you very much, Professor Ali, and also I'd be like to thank to Professor Ronnie Inawan for inviting me, and I'd also like to thank all the organizers of ICT-P 2021 for inviting me and provide me the opportunity to deliver lectures in this international conference. So I wish best of luck, best wishes for this conference. So thank you very much.
Thank you very much, Professor. So ladies and gentlemen, I think we now come to the end of our session. I would like to say thank you, especially to our presenter, Professor Panda from NUS and Professor Bush from India University, and all participants who have been actively involved in this session. It has been a fantastic session, of course, and the pleasure is mine to moderate this section. Just a few quick announcements before I close this section. First is that after this we're going to have break for around 1 hour and 10 minutes. We will be back at 1 p.m. There will be paper presentation session, and we still have a closing ceremony and also best paper award announcement at 3:30. So all participants are encouraged to attend those sessions. I hope you will enjoy the rest of the conference. And now I think it's time to officially close this session. Thank you very much.
Thank you very much, Dr. Ali. Thank you very much, Dr. Panda, Dr. Ghosh. Thank you.
You know I can't smile without you. I can't smile without you. I can't laugh and I can't sing. I'm finding it hard to do anything. You see, I feel glad when you're